So I read this article around a month ago. It's titled, HAProxy reaches 2 million requests per second. And I took a while to process that article, actually read it and understand it. A month later, picking this article up again and reading it again led me to many other questions, right, which I attempt to answer. So I thought maybe this worth talking about it in the podcast and sharing my thoughts on this. Because first of all, what does 2 million requests really mean, right? It's like, what machine can produce 2 million requests first in a benchmark environment? It's like, that's a lot, right? And how does that affect the networking stack? And how does the operating system handle such large quantity? And is this the largest that a proxy or a server can handle? 2 million requests per second, right? Just imagine how much that is, right? Obviously, as a summary, this is the best case scenario, right? That we're demonstrating. I'm going to read the article and then detail and talk about the details about this, right? But that's what I'm going to talk about in this video. I'm gonna illustrate what's the meaning of 2 million requests per second. Specifically, this is HTTP. What kind of hardware did the HAProxy team use to demonstrate that? And what's exactly a request contain here? An HTTP request, what does it have? Does it have TLS? How many connections? And all these questions, we'll attempt to answer them as we progress through the episode. If you're interested, stay tuned. Welcome to the Backend Engineering Show with your host, Hussein Nasser. And this is the show where we talk about proxies, backend technologies, databases, security, backend frameworks, web servers, all kind of backendy stuff, right? So if you like this stuff, make sure to subscribe and check out the podcast. How about we jump into it, guys? So what I want to do here is take a few minutes to summarize the article. So for people who are just interested to know what this thing is. And then I'm going to jump into the screen and then actually read blurbs of the article and explain in details and give my thoughts about each portion. Because I'm just blown away about the things I learned from this article. Things that you really don't think about. You just take for granted. Or maybe just me. Like the number of packets per second. Right? We always think about a request, really. It's just a request. But if you translate that into networking speak, that goes into the OSI model. And eventually end up into the layer 2, which is a frame. And that has a bunch of bytes. And there's some sort of an amplification effect. So if you send at layer 7 1 byte of request, what do you call an HTTP request? Right? It's a very small request. I don't think you can send a 1 byte request. It's a get request, a get slash. Maybe that's the smallest request that you can send. It gets amplified as you get down the stack. Because the TCP stack adds its own header, the IP stack adds its own header, the frames at the MAC layer 2 layer adds its own header, and it sums up, I think it says as 64 bytes minimum, the cost of doing business, right? So think about that. 64 byte leaves your network, and who really sends it out? The operating system, right? And how does the pipe that is leaving your machine sending, I'm talking about just sending the request, how does that pipe, how much bandwidth can it handle? And that's all comes down to what your ISP allows, right? And that's across the internet. But if within a network itself, what's your network card allows as an output input, right? I mean, my machine here is what? I think I'm around 1 gigabit per second. Some network card allowed 10 gigabit per second. And there are networking configurations, even in the cloud. You can configure it to be 100 gigabit per second. Close servers can take advantage of this high bandwidth. So if I say 100 gigabits per second, right, it made me think, how many packets are those? How many packets can 100 gigabit per second really achieve? And as a result, how many packets does not directly translate to how many requests, right? Because a request can have many packets. So all of this is explained in a very nice detail. Willie from the HAProxy community really did a good job explaining all that. But I really love it. But let's summarize what the HAProxy team did here. They said, here's what I'm going to do. I'm going to assume, not assume, they actually did that. A request, an HTTP request is equal 1 packet. So they made that request so tiny such that it fits in a single packet. And I believe what they mean by packet here, IP packets, right? And the response that comes back from the server is also fits into 1 packet, whether a few bytes or not. It's just an empty response. And you might say, Hussein, what kind of test is this? That real life scenarios is never one packet, right? A request, we send all those nasty cookies and headers, and if it's a post request, we send all this body information and we upload files and stuff. So it's easily 7, 8, 10 packets, right, per request. This is demonstrating the best case scenario, which is not wrong. It's just what they are telling you. It's like, okay, this is where you can take maximum benefits. And I kind of like that. So, okay, very clear, right? Another blog, they will not tell you this kind of details. This is really beautiful details. So a request is equal to 1 packet, right? And now, if you think about it, they have to demonstrate HAProxy as a proxy. They placed 3 machines, right? There's the backend, which is a server that is specific benchmarking. They teamed up, by the way, with the Nginx community and team to build this tuning benchmarking tool that's called DB March, I believe, DB Bench, I believe. And they built up this beautiful benchmarking tool that allows you to send a lot of requests, allows you to spin up multiple servers on the same port, obviously, right? You might say, Hussein, how can you spin up multiple servers on the same port? Isn't that just a port conflict? No, Linux allows it, right? Linux does its own load balancing. If you enable this shared object reuse port, you can listen on multiple processes on the same port, and the kernel will load balance packets that comes to that port across these processes. Send packets. Let's be very careful there. You can't balance any packet, right? Otherwise, a packet coming for a single connection might go to another process and it will get confused. This is stateful protocol, right? TCP. All right, so that's what they did. So they brought a machine that is so badass, a 64-core ARM machine from Amazon, right? And they brought 3 instances of that. One is the backend server, one is the proxy, and one is the client that producing these 2 million requests. And they managed to do it. There's a lot of configuration details. A lot, guys. So much configuration details that they went through to achieve that. Because think about it, like, how can you send 2 million requests per second from a client? You have to spin up concurrent processes that allow you to push this kind of data out, right, from your machine first. And the networking interrupt at the proxy level and the server level should be able to receive that. And they achieved a fantastic latency, around Last time I checked, I don't have the article right now, but it's 500 microsecond, not millisecond, microsecond, so half a millisecond, right? And at peak, I think 99.9 latency, it was 64 milliseconds. So it's a little bit, you can see the delay, but that's in Proxy 2, HAProxy 2.3. In the newer version, they slashed this down to 2 milliseconds or whatever, or 6 milliseconds. So overall, it's really, really nice. By the way, guys, I'm not sponsored of HAProxy or anything. I just love this article, and I absolutely will comment on it, right? Just take it as a face value. It's really beautiful stuff here. So 2 million requests per second, right? They went through different iterations to get to the point where they can send 2 million requests, HTTP requests per second, right? And you might say, Hussein, is that a single TCP connection? What does that mean, right? What does it mean, HTTP request, right? That's the same question I had first. Okay, how many connections are we opening? They detail that as well. It's around 1,000 connections, only 1,000 connections between the client and the proxy, and then concurrently multiplexing these requests in those TCP connections, right? And I had so many other questions as well. Okay, what if we use HTTP2? I believe we're going to get a drop when we use HTTP2, personally, if we multiplex these requests. But that's in general. That's what they managed to do. For the details, how about we actually go to the blog article and start piecing it one piece by piece, and then go into the details, right? Let's jump into it. All right, how about we jump into the article, guys? HAProxy forwards. Focus on the word forwards. Over 2 million HTTP requests per second on a single ARM-based AWS Graviton 2 instance. Written by Willie Theroux, April 8, 2021. So it's almost last month, right? So let's read how they started doing that. A few weeks ago, while I was working on an HAProxy issue related to thread locking contention, I found myself running some tests on a server with an 8-core, 16-thread Intel Xeon processor that we have in the lab. Although my intention wasn't to benchmark the proxy, I observed HAProxy reached 1.03 million HTTP requests per second. So they reached 1 million HTTP requests per second while he was debugging an unrelated issue on an 8-core machine. That's impressive, right? 1 million requests. If you can serve 1 million requests, right, and per second, that is fantastic. Obviously, these are tiny requests that takes quick responses, but most production responses take more than that, right? If you're creating a database, that's why you have to minimize the latency as much as possible, right? Very, very critical. These are they measure the overhead of the proxy itself, right? And I forgot to mention, they also measure the direct latency here from the client to the direct server as well. I suddenly recalled all the times that I told people around me, the day we cross 1 million requests per second barrier, I'll write about it. So I have to stand by my promise. So what is writing about it? I wanted to see how that would scale on more cores. So on 8 core, we got 1 million. Do we get on 64? Do we get more? Do we get 8 times 1? Do we get 8 million? Obviously, I wish it works like that, but unfortunately, no. There is so much stuff, guys, that the operating system does that kind of hinders this process, right? Because all these packets that are arrived, the operating system has to sniff them, have to parse them, has to convert them from the physical layer to the data layer to the TCP stack, and then deliver them to the app. So that is latency. It needs it needs cores to achieve that thing, obviously, right? So they're gonna explain in a minute that even though they got 64 Graviton core, they could not use purely all the 64 cores for HAProxy. It's impossible because you need 3 cores to, I don't know, to have like few cores to for the network interrupts, like to listen to these packets that comes, right? You need the operating system to give it something, right? And you need other cores for like SSH, because eventually you're gonna SSH into the thing. You need to look at your results, right? So your SSH, you need some other cores dedicated to other stuff as well, right? Right. So these 64 cores, to give you an idea, their design, each core uses its own L2 cache, and there is a single L3 cache shared by all the cores. So much beautiful. A single cache, 64. So if I hit this core, right, and I cache it to my L3, and I hit the same, almost very similar content or data on that other core, I can benefit from the cache. Powerful stuff, right? Let's continue. I have been extremely impressed by them. He's talking about the machine itself here, going through that, and then going through the steps like, okay, how do you, if you want to compile HAProxy to enable ARM, here's how you do it. I'm not really interested in that. But Synposis. Yes, you have read the title of the blog right. HAProxy version 2.3, when tested on ARM-based AWS Graviton instances, reaches 2.04 million requests per second. Per second, guys. I don't know if nobody is impressed as much as I am, but per second, in a second, 2 million requests has been processed. We're talking request and response. We're talking end to end here, guys. End to end, 2 million requests in a given second. Process like that. HAProxy 2.4, which is still under development, surpasses that, reaching 2.07 and 2.08. It's not that great. It's like, I mean, how much is that? Another 70,000? Another 40,000 requests? Well, they do better. I'm joking, obviously. 2.2 million is a lot. I mean, an additional 40 million is not really, but 2.4 did fix a major bug, looks like it. The latency went, the 99 percentile latency went severely down in 2.4. They fixed it, right? They had in 2.3 HAProxy, they had like a 68, 99.99 per latency. And they dropped that down to 6 millisecond. Great, obviously. All right. So let's look through the graph here. And for people listening in the podcast, I don't know how you listen in the podcast, at the podcast, on the podcast. I don't know how to speak English. We're looking at a graph here with 4 lines. There is the line that shows us the direct request per second, and it shows us also the latency. And when we talk about direct, there's the client, there's the proxy, and there's the backend server. They to test the direct latency, they connected the client directly to the server. That's obviously faster. That's gonna be faster. There is no HAProxy. There is no proxy in the middle taking some precious milliseconds from you, or microseconds, right? There is no middleman to take this hit. If you go directly, it's always faster. They show you how much the latency, and we're looking at around 180, get this, microsecond, not millisecond, 180 microsecond, a round trip, a request and response, directly 180. So a request is taking an average of 180, right? And they're sending around 750,000 requests per second. And what you might say, Hussein, that's very low. That's intentionally low because they dedicated few cores on the client machine for this direct connection to test these numbers, right? Because they want to do some sort of a pivot and test what do they call this? They want a fixed variable to test against direct versus the proxy. So we're looking at 180, around 750 requests per second. But that's very low because it's not compared to them 2 million because they didn't give it as much core as the proxy. Let's take a look at the proxy. The purple line here, the proxy, looking at the latency of the proxy here. And we're looking at 600 microseconds. It's not that bad. It's almost half a millisecond, right? Half a millisecond for a complete round trip from the client through HAProxy. And we're talking about, obviously, a layer 7 proxy here, right? Not layer 4. All the way to the backend. Coming back to the client, 600 microseconds. Fantastic. And then that gives you around 2 million requests per second. Sweet, right? So this is good. And there's a fourth line here. We're looking at the concurrent number of connections. And we're looking at 1,150 TCP connections, right? And this is the connection between the client and the proxy. Because at the end of the day, you can't just send requests nilly-nilly. This is not UDP, right? You have to establish a connection and funnel the request inside the TCP connection. And they had only 1,000 connections to work with, right? Which is, to me, it's very few, right? Usually when you receive 2 million, this is one point. I don't know if they, if HAProxy team mentioned this. I didn't read it. But when you get 2 million requests per second from direct clients, I'm talking, if HAProxy is an ingress that is facing the world, the internet, it's not gonna get 1,000 connection if it's receiving 2 million requests. It's impossible. If you're getting 2 million requests, you're gonna get it from almost distinct connections. You're gonna get it from all over the world. So you're gonna get around 2 million connections. That will be nice to test. How would HAProxy act like an ingress in that case? Because that is a completely different ball game. First of all, can you even open 2 million TCP connection? How much RAM would you need to open 2 million TCP connection? Now, WhatsApp did it. WhatsApp reached what? 2 million, 3 million TCP connections. Right? I talked about that. 3 million TCP connection. That's the definition of concurrency, because you have end users hungry connecting to you. This is a back-end metric here, where you are using a little bit of few thousand requests, 1,000 TCP connection, and then funnel TCP connection, request through these connections, multiplex them essentially, right? It's not really truly multiplexing, right? It's still serializing, but you get the idea. Does that mean this is useless? No. There are use cases that I can think of where you have fewer clients to HAProxy and the actual front end is directly facing clients, actual user client from all around the world. You can do a lot of tricks, but obviously I'm not going to recommend you putting 2 million TCP connections, like all of that. You need to load balance them, right? You need to have many HAProxy fleets. Obviously, people from Asia, in Singapore and Japan should hit a different server than people in North America, than people in Europe. You should have different servers. So you shouldn't really, and you will get to that 2 million if, I don't know, if some influencer in the UK decided to tweet about your servers and all of 2 million people in the UK just decided to hit you. You're going to hit that 2 million in that case. But regardless, you start to distribute as much as possible. At the end of the day, you funnel down on the back end to fewer sets of front-end interfaces, services, nodes, which then funnels back to HAProxy or any proxy that you use, which then lowers the number of TCP connections. Low TCP connections equal happy life, right? Okay, I talked about a lot about this. Let's move on. Here they mention the new project that's called DP Bench has been launched in collaboration with few members of Nginx team. Guys, check this project out. I read about it. Fantastic, right? The thoughts that they thought about all of the stuff I'm talking about here. They thought about all of the things, and obviously more stuff that I even don't know about. All right. Benchmarking proxy is this dedicated for benchmarking proxy. It's so cool that Nginx is working with HAProxy despite them being competitors. Huh? I kind of love that. I like that. It's like an all-star soccer game, right? Kind of a thing, like a World Cup, like all the elite come together. I like this. Cute. Methodology. All right, so they talk about in this benchmark, we're testing HTTP request per second and then end-to-end request latency at the 99.99 percentile, which I talked about here. Here they talk about the instance size. We used an AWS C6GN 16x large virtual machine instances which are 64 core machines from the C6GN series. Guys, by the way, I know nothing about machines and hardware, guys. So these numbers mean nothing to me. Maybe to you, if you're a hardware engineer or if you're like into PCs and building PCs, you're probably like freaking out right now. That's like, oh wow. But to me, these numbers don't mean anything. So probably it's obviously a great machine with access to 100 gigabit per second network bandwidth. Very critical here, because I'm going to talk about this. 100 gigabit per second. They're compute optimized using Graviton processors and are built in application require high network bandwidth. The instance size is used for the client, proxy, and server. So 3 instances. I first started with a 16 core, then a 32 core. So he started moving from 16 core to 32 core. And thinking this could have been enough. A direct test from the client to server without HAProxy between. All right, so they tested first from the client to the server. Let's see, okay, what's the maximum can we get? Because let's forget about HAProxy. Directly from the client to the server in the same network, 100 gigabit per second. How much can we get? So they did a test, right? They're not testing requests yet. They're testing packets per second. It's like I talked about that in the summary. What does that mean? Because like, how much packets can I eject from my client? How fast can I eject packets from my client to my server? Right? And that's another problem. 8 only. He's disappointed. Will is disappointed with an 800K packet per second. I'm gonna say Will is spoiled. 800K. He's not happy with an 800K. I'll kill for 800K packets per second. But yeah, that's essentially low. And you might say, why low, Hussein? 800K, 800,000, almost 1 million packets per second, right? So let's talk about packets per second, guys, here. And let's read this and then can talk about packets per second. I then decided to go for the full on 64 cores on a dedicated host. So does that mean it's not virtualized? I guess that's what it means. This time I got my 4.15 million packets per second, right? So he got 4 million packets per second sending from the client to the server. I guess there is a benchmark that does that. I just think how many packets per second. I think it means IP packets here, low-level IP packets, right? 4 million packets per second, right? In the same network. And thought it would be sufficient since I really only need 2 million packets to achieve 1 million requests per second, accounting for 1 packet for the request and 1 for the response. That's what I mentioned in the summary. The HTTP request that he's making is essentially tucks nicely within a single IP packet, which is almost never the case in a real world scenario, right? That's why he's describing the best case scenario. And that's not wrong. It's just something you have to understand. So in your case, you might not get 2 million. You're going to get 800 or 1.5 million. Depends on the load and consumption. And that's fine. That's great too. 1 million. That's amazing. Let's talk about this a little bit. So let's open this. Let me open the calculator a little bit here and do some math. Let's open the calculator. Can we make this bigger? Can this make this bigger? This is as big as it gets. All right. How big is a packet really? A packet, last time I checked, adds 20 bytes. An empty packet in the TCP, an empty, no data, adds 20 byte header in the, let me get the numbers right, correct, because I actually stripped them from Wikipedia. An empty packet, right? An empty TCP packet, no data at all. You get an amplified bytes of 20 bytes on the TCP stack, which is layer 4, and then you add another 20 bytes on the IP frame and the IP packet on the IP layer 3. So that's 40, and then another 24 on the frame on layer 2. So that's total 64 bytes with no data. Let's be conservative and say my application HTTP is 64-bit. Obviously it's less, 64 byte. So that means a single request is 128 bytes. So sorry, a single packet is 128 byte. Okay. How much packets could I send on 100 gigabit, theoretically speaking? Let's do some math. 100 gigabit, make sure this is gigabit, so you have to divide it by 8, right? To make it byte. 100 gigabit network is 12.5 gigabyte, right? So you can send 12.5 gigabytes in a single second on this beautiful network that Willie has. 12.5 gigabyte, right? Now, you multiply this by 120,004 to get 128,000 megabyte. And you multiply it by another 120,004, you get blah, 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 blah. What is this number? This is 13 million kilobyte. And then you multiply by another 1,024 and you get this much bytes. This is 13 billion bytes, 421 million and 772,000 bytes. You're going to divide that. This is the number of bytes that you can eject from your machine if you have a 100 gigabit network. You divide that. How do I know how many packets? I divide it by 128. And you're going to get a whopping 100 million packets. 100 million packets. This is all theoretical based on math, right? If you have a 128 packet size, right, which is a 64 byte HTTP request, you can get up to 100 million. Let's just simple, 100 million packets. This machine is not even close to how many packets you can get. This machine gave you 4 million. So this is not just the machine. The operating system cannot possibly output more than 4 million packets per second. So we still have so much to go. You don't need more than 100, to me, in my opinion, 100 gigabits. It can give you 100 million if you are efficient enough. But it looks like today, with the latest tech, we can output up to 4 million packets per second. Where, theoretically speaking, we can reach 100 million packets per second. Again, this is all my math. I might have done something wrong, but right. And then obviously this is very hard to achieve because there is latency. There is processes eating through this, from the operating system to the network side to the hardware to the motherboard to the operating system stack to the application stack to all other stuff to the CPU. So if we can reach 4 million, which Willie did on a 64 cores, because you need CPU to push this thing out, right? You need core, you need compute to push it out, right? Yeah, so he reached 4 million packets, which translates to 2 million requests. Here's one of the things that I absolutely didn't know anything about. Interrupt affinity. Apparently, who knew? But to enable networking to send data outside of your operating system to the world, you kind of need some operating system help, and you need cores to do that. You need cores. Yeah, it's not free. Duh. Obviously, I didn't think about it, but it's so fascinating to read through this. I'm going to let you read through this, but I'm going to just read part of this. It took me a while to figure out how to completely stabilize the platform, because while virtualized, there are still 32 interrupts assigned to the network queues. There is a network queues, apparently, right? Delivered to 32 queues. So there's a network queue going to the 32 core CPUs, and it can work only with 32 cores, right? So this could possibly explain the lower performance with a lower number of cores. The lower number of cores, the lower the performance, because there's bottlenecks, right? 32 queues can sound a lot to some reader, but speaking about 100 gigabit per second networking here and millions of packets per second, at such packet rates, you definitely do not want any user land process to hit one of these core during the middle of your test, right? Because you don't want these CPUs are busy. These beautiful cores are busy serving your network latency. They're just sending out data. If you are executing your stinking Node.js Express and then taking precious time from these cores, the test's gonna suffer. So he's going through, it's like, how did he solve this? He kind of dedicated, eventually he said, okay, I'm gonna dedicate 16 queues to 32 cores, right? Two interrupt per core, essentially. That's what he did. And then showing you how to do that, essentially. And then going through the network topology. This is very interesting. So let's talk about 64 core. How did Willie divide this 64 core? He reserved cores from 48 to 64 to 63 to the network interrupts. So you have 16 cores dedicated just for networking stuff, because the operating system need to push these packets out. And cores from 2 to 47 are the cores dedicated for the actual running process, this is HAProxy and the proxy machine. This is the server, which is whatever the server they're using, and the client process that spits out all this content in the client machine itself, right? Very interesting stuff. And CPU number 1 is used for the reference, right? They're hitting the direct connection between the client and the server. This is the controller thing. Is they want to connect from the client directly to the server to control this behavior. All right. So that's how they broke things up. And core 0 is reserved for SSH, to connect through machines and look at them. You need to give the SSH some memory, right? Some cores to work with. The CPU is important, apparently. So obviously, the first thing to do here, if you have 46 cores to work with as an HAProxy, what do? 46 cores on the backend. So we're looking at the backend, the server. There's this thing called HTTP term, which is their HTTP server. That is in the backend. The first thing they do is, you need to max out how many connections can you achieve, how many file descriptors. Update the user limit using ulimit-n 100,000, as much as you can. And then spin up using this task set, spin up this much HTTP instances, right, through cores 2 to 47, right, because that's where the cores we're going to work with, on port 8,000. Obviously, since we're listening on the same port, definitely you have to configure this shared object port reuse to listen on the same port, right? And then all these processes are dedicated for these cores. Beautiful stuff. And they do the same thing with HAProxy, again, from 2 to 40 from core 2 to 47. That's dedicated for proxy. And they're running, they're showing the code here. They do the same thing for the proxy. They do the same thing for the H1 loader, which is the client that spits out this much connections, right? And then the client here, they specify how many TCP connections to connect to. 1,150 is the maximum current connections here. And we talk about also the controller process, which they call the reference, connecting directly from the client to the backend immediately, directly. And that is using 128 connections. They're opening to 128 connections, and they're using one single core. They give it only a poor thing, only one core. And it did achieve around what? 200 microsecond. That was like amazing. Now we're going through the result. HAProxy 2.3. Let's look at 2.3 and look at 2.4 and then end the video. I know it's a little bit long video, guys, but I'm just fascinated by this. Fascinated. Absolutely fascinated. This is the same graph that we looked at. We're looking at 1,150 concurrent connection between the client and the HAProxy, and we're looking at 600 latency, microsecond latency, right? And around 2 million requests per second, right? And the direct connection between the one to the second is obviously peaking at 120 concurrent connection and 120 microseconds. Wow, right? And then they show you another graph, which is the 99.99949 latency for 2.3. Can you take a guess? It's a little bit yikesy in 2.3. It's 68 millisecond. That's it's quite a lot, right? For something in the network itself. But I'm fine with it, to be honest. 68. Woo. But look at that. That's the maximum 16. That means 99.9999 requests are less than 68 milliseconds. That's what it means, right? But HAProxy team says, you know what? That's not acceptable, because the direct is one millisecond. That's the direct 99.99 latency. Wow, right? So they worked on 2.4. They fixed a lot of, did a little magic, and they dropped the latency from 68 down to 1.8, which is just fantastic. They fixed so much stuff. I'm not going to go through the details. I'm going to reference the article below, guys, if you want to read more about it. But they essentially took full advantage of that. All right, let's talk about TLS. The above that we discussed was unencrypted HTTP. So the first question is, okay, how does this behave in TLS? Guys, and when I read this, like it says, it's not going to have any effect, right? Why? Because TLS is a one-time cost. And based on what they are doing here, the 1,000 connection, you're going to pay the price of TLS 1.2 or 1.3, right? It's just a one-time price. You're going to establish the TCP connection. Once they are open, you're done. HAProxy is happy. Now you can funnel all the requests you want. The only cost, that was the TLS handshake is the expensive thing, right? Especially if you're using, depending on the cipher, the whether you're using a Diffie-Hellman, how many bits in Diffie-Hellman exchange, and whether you're using elliptic curve Diffie-Hellman, how many bits there, what's the bit size in the certificate, right? The private public key of the certificate, are you using RSA? How much bits are there? It's like, is it 4,000 bits? That's obviously slow, right? And that's what they're using. They're using 2,000 RSA. But I had a conversation with Willie, and I said, like, oh, guys, if you use the certificate with such an elliptic curve DSA, like the digitally signed, I forgot what the algorithm, which uses list bit, essentially using elliptic curve instead of RSA. So you have fewer bits, right? Instead of higher number of bits. So that's obviously faster, right? Dealing with the lower number of bits. And they said, doesn't matter. Hussein, doesn't matter. Because this is like a one-time cost. You're going to hit it and then it's going to swallow away. It's going to gone, right? Yeah, you're going to hit it in the beginning, just the establishment of the connection. But once you have the connection, you're encrypted. The extra cost that I can think of is in the algorithm, the symmetric algorithm itself, which is EAS. This I see having an impact, right? But it looks like we didn't give much. We had like around 600 microseconds. It's almost the same, right? It's the same thing. TLS terminated, all that jazz. The number of requests dipped a little bit, right? From 2.07 to 2.01. So it dipped around 0.07, whatever, 70 requests, 70,000 requests. Not much. So AES is really good. And I mean, you can use Cha-Cha, which I believe it's faster. Cha-Cha is faster than EAS, they claim, using a little bit lower number of bits. That's what I heard. I don't know if that's true. But yeah, I think Cha-Cha is a little bit popular with kids these days. And they show here the obviously the latency. We're seeing the latency a little bit pumping up with TLS up to 6 milliseconds. That's kind of understandable because we're using TLS, we're terminating TLS, so there's an additional overhead. I'll take it. I'll take the 6 millisecond. That's nothing. So we're going through analysis here and all the details, but this is fantastic article. Really, I really suggest you guys read through this. I learned so much through reading, just through this. It took me a month just to process the amount of information there. And I'm pretty sure I missed a lot of stuff. So thank you to the HAProxy team for this fantastic article, sharing their knowledge, sharing their Tyler-based knowledge. Keep sharing knowledge, guys. This is beautiful stuff. Guys, if you enjoy this kind of things, click on this video and watch it. I think you're gonna love it. This is talking about actual HAProxy, how to set it up and all that jazz. All right, guys, I'm gonna see you on the next one. You guys stay awesome. Goodbye.